So next, another type of scheduler we have, that is fair share scheduler. So some set of users may want the certain amount of CPU time on a guaranteed basis. So in the previous scheduling algorithm, that is a normal scheduling algorithm, where we saw each and every process is getting equal amount of time. So whether it has how many number of instruction or how long it is going to get executed doesn't matter. It is going to allocate a specific amount of time. For example, if I have 4 processes in my system, and all 4 processes will get equal amount of time. That means 25% of CPU time. If I have 10 processes in my system, each and every process will get a 10% of CPU time. But in case if a particular user wants to give more priority to a particular process, then at that time we need to use fair share scheduler. So some set of users may want certain amount of guaranteed time. So for that we have to use fair share scheduling. So the principle is user community is divided into set of fair share groups. So here we are going to divide the processes into different groups, and based on the groups the processes are going to get executed. So the system allocates its CPU time proportionally to each group. So let's see one example. For example, 4 groups are there. So each group has 1 process, 2 process, 3 process and 4 process. So the first group has 1 process, second group has 2 process, third group has 3 process, fourth group has 4 process. So we have divided into 4 groups, and regular scheduling algorithm gives 10% of CPU time for each process. So the totally we have 10 process here. Totally we have 3, 6 and 10 process here. So 10 process will get 10% of time. But here there is no specific amount of time will be given for, or specific importance will be given for a group. But if you divide these groups in these process into groups, and for example I want this first group to give more priority or more importance to be given to this particular process, then I can put it in a particular group and other process in other groups. So that fair share scheduling will ensure each and every group gets that specific amount of time. For example, 25% of CPU time for each group. So this group will get more benefited, this group will get benefited lesser than the first group, lesser than the second group and lesser than the third group. So based on this, some assured time will be given for each and every process. So whenever you have fair share scheduling, there is a slight change in the priority calculation. That is, fair share group priority is equal to CPU by 2 plus group CPU by 2 plus base level priority. So there is one more count added, that is group CPU. So group CPU is also getting added here. So let's see one example. This is the example for fair share scheduling. So fair share scheduling, as we discussed, here we are going to have groups for every process. So here I have 3 processes. So process A, process B and process C. Process A belongs to group 1, process B and C belongs to group 2. So here we have 2 groups, and process group 1 has 1 process and group 2 has 2 processes. So fair share scheduling means the CPU time will be divided into groups. For group 1, 50% will be allotted. For group 2, 50% will be allotted. So the group which has less number of processes will be benefited more. So as per this example, we have group 1 and group 2. Group 1 has only 1 process and group 2 has 2 processes. So group 1 will get more benefited. Let's see how it is going to get executed. And here there are the formulas to calculate the decay CPU. That is a recent CPU usage, that is CPU by 2, and decay group, that is group by 2. Then priority calculation, there is a slight modification. The priority calculation, it is decay CPU by 2 plus decay group by 2 plus the base level priority. So here also we need some of the parameters to execute to solve this problem. That is, base level priority we need. Base level priority for this problem is 60 as per this example, and this clock interrupt is once again 60 times per second. So when a process is getting executed for 1 second, 60 times this clock interrupt will happen. So the count will be incremented from 0 to 60. And then here also once again the time quantum for each and every process is 1 second. So it is not given. So if it is not given, then it means the time quantum for every process is 1 second. So here I have given the timeline for each and every process. So here I have 5 time quantums are given. So when for after every time quantum, the priority is going to get calculated again, and then we are going to decide which process to get executed based on the priority level. So the same information I have mentioned here. Process A belongs to group 1 and process B and C belongs to group 2. So let's see how it is, how we have to solve it. So once again we have to decide the process execution based on the priority. So here all the processes are having equal priority, that is 60, and all process has arrived at the same time. So we can decide any one process to get executed for the first time. So for the first time, I'm considering this group 1, the process A which belongs to group 1 is getting selected for execution. So when this is getting selected, when this process is getting executed, the CPU count as well as whenever that particular group is under execution, the group count will also get incremented. So as per this example, so this process is getting executed. So this CPU count will get incremented. CPU count will get incremented based on this count. So 60 times per second. So this process is going to get executed for 1 second. So for 1 second, 60 times it will get interrupted. So 1, 2, 3 up to 60. The CPU count we have to write it as 60. And then the group count will also get incremented because this group is under execution. So 1, 2 and up to 60. So now we have to calculate the decay CPU, decay group and the priority for all the process. So for the first process, for the first time quantum 1, we have to calculate the priority for every process. First I will calculate the decay CPU for process A. I am calculating the decay CPU. Decay CPU is equal to CPU by 2, that is 60 by 2 is equal to 30. Then I have to calculate decay group. Decay group is equal to 60 by 2 is equal to 30. So I will write the answers here. 30 is the decay CPU and 30 is the decay group. And for other process it is 0, 0. There is no, it is not incremented because those things are not get executed. So 0, 0. So now I have to calculate the priority. To calculate the priority, we know the formula. So priority is equal to decay CPU by 2, that is 30 by 2, plus decay group by 2, that is once again 30 by 2, plus 60. Base level priority will not change. Always the base level priority is 60. So here the answer is 15 plus 15 plus 60. So we'll get the answer as 90. So 30 plus 60 will get answer as 90. So the priority for process A is 90. Priority for process B, there is no change. So 60. Priority for process C, there is no change. Once again it is 60. So once again we have to select the process, highest priority process based on the priority. So here we are not talking about the groups. Whenever you want to select a process, the process will be selected based on the priority of each and every process. So now if I see the process priority for process A is 90, which is lowest priority. Process B has highest priority 60. Process C is also having equal priority. So any one process, any one of these processes can get executed. So I will say process B is getting executed. So when process B is getting executed, process B and C belongs to same group, that is group 2. So when process B is getting executed, the CPU count will get incremented. 1, 2, 3 up to 60. When process B is getting executed, it belongs to group 2, so group count will also get incremented. But here process C is not getting executed, only one process can get executed at a time, but this group is getting executed. So process B and C belongs to group 2. So when process B or C, any one of the processes getting executed, the group count for both processes will get incremented. So process B is getting executed, that means group 2 is under execution. So this group count will also get incremented. Got it? So group count is getting incremented here. So let's calculate the decay CPU once again. this is for the second time quantum. Process A, first for process A, we have to calculate the decay CPU. So decay CPU for process A is already we have written as 30. So 30 divided by 2, it is 15. Here once again 30 divided by decay group, it is 15. Here 60 divided by 2, it's 30. 60 divided by 2, 30. So decay group and decay CPU for every process we have to calculate. And then 0, and then here it is 30. So decay group. Now we have to calculate the priority for process A. So priority for process A, priority is equal to decay CPU by 2. So what is the decay CPU value? Decay CPU value is 15. So 15 by 2 plus 15 by 2 plus base level priority 60. So it's equal to, we have to take the whole number alone. It is not 7.5, it is just 7. 7 plus 60. So we'll get the answer as 74. 14 plus 60, 74. So 74 is the answer. That is a priority for process A. Now for process B, we have to calculate. It is priority is equal to 30 by 2 plus 30 by 2 plus 60. We'll get 15 plus 15 plus 60. So the answer is 90. So the priority for process B is 90. So we have to calculate for process C. So process C, the priority is equal to decay CPU by 2. Decay CPU is 0 by 2 plus decay group by 2. Decay group is 30 by 2 plus 60. So 15 plus 60. 15 plus 60, it is 75. We'll get the answer as 75. Always remember, whenever we are dividing a number like this, 15 divided by 2 or any other number, even whenever you are getting 0.5 or 0.2, you should not take the decimal values. We should only take the whole numbers. That will make a lot of difference here. So as per the second time quantum, we are getting the priority values as 74, 90 and 75. So which one is the highest priority? That we have to check. So 74 is the lowest number. That means this is the highest priority. And this is the lowest priority and this is the second highest priority. So this has highest priority. So process A will get executed now. So right now process A is getting executed, and so from the last number we have to increment. So 16, 17, and it is getting incremented, and it is 75. So process the CPU group count is also getting incremented, 75. And these two processes are not getting executed. So just as it is, it will be there. But we have to calculate the decay CPU now. So 75 divided by 2, that is a decay CPU for process A. So 75 divided by 2, you will get the answer as 37. So here once again 37. Here you will get answer as 15. 30 by 2, 15. And here it is 0, and here it is 15. So now we have to calculate the priority for the third time quantum. The third time quantum, we have to calculate the priority. So for process A, priority is equal to decay CPU by 2. Decay CPU is 37. So 37 by 2, decay group by 2, that is 37 by 2 plus base level priority. So base level priority is always 60, it won't change. Then calculate it. So 37 divided by 2. So 37 divided by 2 is 18.5, but you should take only the whole number. So it is 18. 18 plus 60. So 18 plus 18 is 36 plus 60 is equal to 96. So 96 is the priority for process A. Then for process B, to calculate process B, so priority is equal to decay CPU by 2, 15 by 2 plus decay group by 2, 15 by 2 plus 60. So 7 plus 7 plus 60, it is going to be 74. 74 is the priority for process B. Then for process C, process C is decay CPU is 0 by 2 plus decay group is 15 by 2 plus 60. So 7 plus 60. So it will be 67. So for the fourth time quantum, we have to select the next process to get executed based on the priority. So 96, 74 and 67. So 67 is the highest priority, 74 is the second highest priority, 96 is the least priority. So 67, this highest priority process is getting selected to get executed. So the CPU count will get incremented 1, 2 and goes on up to 60, and here plus 60, sorry 16, 17, it goes on up to 60, so it is 75. Okay, these are the CPU count and group count. So when this group is under execution, the group count should get incremented for both the process, because process C and B belongs to group 2. So the group count for process B also should get incremented. So it is 16, 17 up to 75. And this CPU count will not get incremented because this process is not under execution. And these two counts will not get incremented. Now if I write the CPU count, decay CPU count once again, it is 37 divided by 2. 37 divided by 2, it is 18. 18. Decay CPU for process B, 15 divided by 2, it is 7. And for 75 divided by 2, it is 37. And here 60 divided by 2, it is 30. 75 divided by 2, it is 37. So these are the decay CPU values. Now based on the decay CPU value, we have to calculate the priority. So priority is equal to decay CPU by 2 plus decay group by 2 plus base level priority. So here if I calculate it, decay CPU by 2, decay group by 2, it is 9 plus 9, 18 plus 60. So 78 is the answer. And here it is going to be 3 plus 16, sorry, 3 plus 18, 21 plus 60, 81. And here it is 15 plus 18, 33 plus 60, 93. So now once again we have to select the highest priority process, 78, 81, 93. So 78 is the highest priority. So 78, the process 78 process which has 78 as the highest priority will get executed. So process A is getting executed now. So process A is getting executed. So the CPU count and group count will get incremented. 19, 20 plus 60. Just whatever the number we have plus 60. So you will have the number of 78. And here once again 19, 20 and 78. So this process is not getting executed, so we don't need to touch it. So process A belongs to group 1. So only these things we have to modify. So once again we have to calculate the decay CPU for every process. It is going to be 78 divided by 2 is 38, 39, 39, 39. Here 7 divided by 2, 3, 37 divided by 2, 37 divided by 2, it is 18, 15, 30 divided by 2, 15 and then 18. Now once again the priority has to be calculated. If we calculate priority, 39 divided by 2, we will get the answer as 19. So 19 plus 19, it is 38. 38 plus 60, 98 is the priority. And here 3 divided by 2, we will get answer as 1.5, but we have to take 1 plus 9, it is 10. So 10 plus 60, the answer is 70. And here 7 plus 9. 7 plus 9 is 16 plus 60, 76. So now process B will get selected and B will get executed because B has the highest priority as 70. So now this will get increment. This will get selected and it will get executed. 63 and this is 78. So this is how the process are going to get executed. So this is what fair share scheduling means. So processes are grouped under different groups. Group 1, Group 2. Group 1 has process A, Group 2 has process B and C. So we have 3 counts: process priority, CPU, priority is 60 for every process in the initial stage, and CPU count and group count is incremented whenever that particular process or the group is under execution. So we started with process A. Process A is getting executed, and this count is getting incremented up to 60 based on the clock interrupt. So it is 60, and CPU count, group count is also getting incremented to 60. And then we calculate the decay CPU. After every time quantum, you have to calculate the decay CPU first for every process and take and write it here. So whatever the value we got, divided by 2. So that is 60 divided by 2, 30, and we have written everything. And for the second time quantum, we are executing this process B. Process B is getting executed here. So this CPU count is getting incremented for process B, and group count is also incremented for process B. So process B and C belongs to same group. That is why process C group count is also getting incremented, even though that process is not getting executed. Similarly, whenever process C is getting executed, at that time the group count for process B is also getting incremented. So after completing all these things, we have to write the process execution steps, like how the processes are getting executed, in what order the processes are getting executed. So if you see, process A is getting executed first. Process A got executed first. Process B got executed next. Once again process A, then process C, then process A, then process B. So in what sequence the process is getting executed, that also we have to take and write. So as per the sequence, it is A, B, A, C, A, B. So process A is getting executed more than process B and C, because process A belongs to group 1, where only one process is allocated. Process B and C belongs to group 2. So process A is getting more importance than process B and C. So this is called fair share scheduling. So in this example, we have the time quantums here: process A, process B, process C. So the base level priorities are 60. We have a CPU count, group count, CPU count, group count for every process. So process A belongs to group 1, process B and C belongs to group 2. So process A is group 1, so this is getting more priority, more time than process B and C. So whenever a process, whenever a group is getting executed, that group count will get incremented. Whenever the process is getting executed, the CPU count is getting executed. So based on that, we have seen this example. So there are group count and process CPU count, and then we calculated the priority, and then the process executions are done. So real-time processing. So we have seen this process scheduling, whether it is applicable, whether this Unix system is applicable for real-time processing or not. So actually the real-time processing implies the capability to provide immediate response to specific external events. But they cannot guarantee that kernel can schedule a particular process within the fixed time limit. So there is no guarantee for kernel to schedule for a fixed time, or the kernel should be preemptive. So we know that the process which is executing in kernel cannot be preempted. So these kind of limitations makes the Unix system not suitable for real-time processing. And there are some system calls available for times. There is stime to set the value, so to set the time, and time tlock, that is time retrieves the time as set by the stime system call, and then times system call, then struct, there is a structure available for the time. So these are the system call which is required to set the time in your Unix system. So here to set the user time, this kernel time, cumulative user time, cumulative kernel time. And these are the functions of a clock. So what are the functions of a clock? We discussed about clock interrupt handler, and these are the functions like it restart the clock, schedule invocation of internal kernel functions, provide execution profiling, gather systems, keep tracks of time. So this is going to maintain so what are the how the process is getting executed, how long it is executed, and the time quantum and time slice, everything is being maintained by this clock. So the algorithm for the clock is also shows the same, how it is maintaining the time. So next one is internal system timeouts. There is a timeout, or there is another thing called as callout table is available in your system. Callout table is required whenever a time arrives, whenever a process is executing, whenever it reaches a particular time, there is a process which is going to get executed. So that is called as time to fire. So each and every process, for example, here there are some process given ABC, and the process ABC are assigned with the time to fire, that is -2, 3 and 10. So whenever this time has arrived, whenever it reaches a particular time, then that particular process will get executed. So this is to maintain the time for the entire system. So this is a part of the clock handler, and that process will get automatically get executed whenever this time to fire arrives. For example, if process B is here, and process B is the value is 3, and each and every time quantum that the process time will get decremented. So when it reaches 3, and then this process will get fired. When the time reaches -2, then this process get fired. So similarly, different other process will get executed, and it will get fired when the particular time reaches in the callout table. Then we have another two things, that is profiling. Profiling is to maintain the time, how long that particular process is executing in the system, or to record the time in your system. So we have the system called profile, buffer size, offset, and scale. So these are the values we are providing to get the profiling of a particular process. And accounting and statistics, that is also to maintain the time, and to keep the time the process are getting executed. The kernel clock handler is going to maintain everything. So as a summary, in this chapter we discussed about process scheduling algorithm, where the best process is getting picked by the process scheduling algorithm. Then we discussed about two types of process scheduling. One is a normal process scheduling with an example. The next one is a fair share scheduling, where the process are divided into groups, and then it is getting executed. Then controlling process priority, which is done by the nice value. Nice value is being provided for calculating the priority, and then it is done. Then real-time process time processing, where we discussed whether this kernel system, Unix systems, are suitable for real-time processing or not. Then we discussed about system calls for times, and then finally we discussed about clocks and other system calls. Thank you. If you have any doubts, you can comment below this video, so that I can clarify the doubts in the next video. Thank you.